today we're going to talk about some very basic things. So we're going to start with talking about what a proof is, how we can prove some basic facts in propositional logic and then first order logic. And then we're going to define the set of natural numbers. So we're just going to build numbers and see what numbers are. Okay. So let's start with the simplest type of logic that we have, and that's propositional logic. Oh, by the way, you don't need to take any notes because I will give you these files, and also the TAs are writing the class notes for you, so you can just download them from Canvas. So just relax and listen to what's going on. You don't need to take any notes. Okay. Oh, and I will also record all of these sessions and put them on YouTube and also on Canvas. Okay. So what is propositional logic? Basically, what is a proposition? A proposition is basically any sentence that can have some sort of a validity judgment, any sentence that can be true or false. Okay. So because we're computer scientists, for us, true means 1 and false means 0. So throughout this course, I'm going to use these notions interchangeably. So when I say something is 0 or false, they're the same thing. So a proposition is something that can be either true or false. So if I want to give you some examples of propositions, one example would be the temperature is 25 degrees right now. Okay. Now, I don't know if that's true or false. I don't have a thermometer, but it is either true or false. It's one of those two things. But if you cannot assign any kind of truth or value judgment to a sentence, then it's not a proposition. So if I say something like, I don't know, an imperative sentence, if I say close the door, that's neither true nor false, right? So we don't consider those kinds of sentences. We only consider sentences that can be either true or false, and we call them propositions. And generally speaking, we use lowercase letters to show propositions. So I use P, Q, R, so on to show the propositions. So for example, again, P can be the proposition that we are in classroom, let's say 2, 4, 5, 6. Okay. Is this a true proposition or a false proposition? How many of you know where you are? So this is false. Yes. But of course, I'm not just interested in atomic propositions like this, and I call it atomic because I cannot really break it down into smaller propositions. It doesn't have any parts. It's just an atomic thing. It's an assertion that I'm making. It can be true or false. But this is not very interesting. What's interesting is how can we combine different atomic propositions and get more complicated propositions. So here's one thing I can do. I can do negation. So these are the operations that I'm going to allow. And my first operation is just negation. And if I have a proposition P, I show the negation of P like this. So, and the way I read it is that it is not the case that P. Okay. So if P is that we are in classroom 2, 4, 5, 6, negation of P would be we are not in classroom 2, 4, 5, 6. Or to be more pedantic about it, it is not the case that we are in classroom 2, 4, 5, 6. Okay. So that's how I create negation. Now, one thing we do very often in this course is that we draw truth tables. So let's do something like this. Let's say I have my P, and now I have negation of P. Now, P can have different values. Maybe P is 0 or 1. So maybe P is false, maybe P is true. If P is 0, then negation of P is 1. If P is 1, then negation of P is 0. This is very easy. So because at the end of the day, we are either in this classroom or we're not. Right? If P is false, if this sentence is false, then its negation has to be true. Okay. Again, I'm telling you, this session is not representative. The rest of this course is not going to be easy like this. Okay, so this is what I call a truth table, and this is just negation of P. And sometimes instead of saying negation of P, I just say not. Okay. But I like to do some other operations as well. And actually, I like to be able to combine several different atomic or non-atomic propositions. So I would like to also be able to do disjunction. Now, disjunction is basically the same as OR. So I can write something like this. This is disjunction of P and Q, or again, to be nicer, we just say P or Q. And what it means is that at least one of P and Q holds. Okay. Now, it doesn't mean that exactly one of them holds. It means that at least one of them holds. So it's possible that both of them are true. So for example, let's say Q is the statement that you are a first-year student. Okay. So now P or Q would be the statement, the whole statement that we are in this classroom, and sorry, not and, or you are a first-year student. So P or Q would say that we are in classroom 2456, or you are a first-year student. It's not exclusive. It doesn't mean that both of them cannot happen at the same time. So if I want to create a truth table for it, it would be something like this. So I have to look at the value of P, I have to look at the value of Q, and this is the value that I will have for P or Q. So P can be true or false. Q can also be true or false. So I just do this. This gives me all the possible combinations for P and Q. By the way, at some point in this course, we're going to talk about counting, and then we will talk about how we can create all of these and count how many possibilities we have and things like that. But right now, I just wrote down all the 4 possibilities. So if P is false and Q is false, then P or Q is false. So basically, if we are not in classroom 2456 and you are not a first-year student, then it is not the case that we are in classroom 2456 or you are a first-year student. Okay, very easy. Now, if one of them is true and the other one is false, then P or Q will also be true. So if we are in classroom 2456, but you are not a first-year student, then if I say that we are in classroom 2456 or you are a first-year student, I'm saying a true sentence. Okay. The same thing happens if the other one is true. But now, if both of them are true, again, the result of the disjunction is true. So when I say we are in classroom 2456 or you are a first-year student, if both of them are true, what I said is still true. Okay. So this is what we call disjunction, or basically this is logical OR. And then, of course, as you would expect, we also have conjunction, which is logical AND. So I have P and Q. Now, P and Q is true only when both of them are true. Okay. So even if one of them is false, P and Q will be false. So I can again do the table. This is actually painful, and it gets more painful as we go forward, because soon I will have more than 2 variables, and then this table gets really long. So 0, 1, 0, 1, 0, 0, 1, 1. Okay, so if both of them are false, P and Q is false. If one of them is false, P and Q is false. The only case that P and Q is true is if both of them are true. Okay. You can think of these statements as some sort of a promise. So when I'm doing disjunction, when I'm saying P or Q, I'm promising that at least one of them is true. When I'm doing conjunction, when I say P and Q, I'm promising that both of them are going to be true. Okay. Nice. So I think you've already had all of these things in high school, hopefully. But we have one more thing, which I should talk about, and that's implication. Okay. So I write it like this. And you can read this in many different ways. You can say P implies Q. You can say if P, then Q. And that's normally the way we say it in computer science because that's the way it works in programming languages. So I would just say if P, then Q, or sometimes I don't even say the if, I just say P, then Q. Okay. And basically, this is also a promise. It's a promise that whenever P holds, Q will also hold. Okay. So I'm saying if P holds, then Q also holds. But this is a conditional promise. I'm not making any promise to you in the case where P does not hold. Okay. So let's now create a truth table for this. So I have P, Q, P implies Q. Again, 0, 1, 0, 1, 0, 1. So let's look at the last case first. In this last case, the premise was true, so P is true, and the conclusion is also true. So I promised to you that if P holds, then Q holds, and I kept my promise. So in this case, P implies Q will also be true. So basically, read it like this. I'm promising that if we are in classroom 2456, then you are a first-year student. Okay. Now, weird promise to make, but I'm making that promise. Now, if it turns out that we are actually in that classroom, and it turns out that you are also actually a first-year student, then I've kept my promise. Right. Now, the other case, the other simple case is this case, when P is true and Q is false. So in this case, I've broken my promise, and P implies Q is false. So if we are actually in that classroom, but it turns out you're not a first-year student. So that's a case where I have broken my promise. Okay. Now, the other two cases are actually much more interesting. These are the cases where the premise is already false. So I promised you that if we are in this classroom number 2456, then you're a first-year student. But as you know, right now we are not in this classroom. So the conditions of my promise are not satisfied at all. So my promise is kept by default. I'm just promising that if this happens, then that other thing should also happen. But the condition was not happening in the first place. So in both of these cases, P implies Q is going to be true. Okay. Now, these two cases are sometimes strange for people. So try to make sure you have the correct intuition about this. Again, just think of it as a promise. I'm promising that if P holds, then Q also holds. And this promise will be false only if P holds and Q does not hold. In any other case, I have kept my promise. Okay. So now, of course, I can combine all of these operators and I can create all sorts of weird combinations of different atomic propositions. So if I have a bunch of atomic propositions, P, Q, and R, I can write something like this. P and not Q implies R. And then I can say all of this implies T. And this all makes sense. Okay. Now, you need to put the parentheses there because otherwise you don't know the order. But generally speaking, we always say that not takes precedence over everything else. And then the second level of precedence is given to and or from left to right. And implication has the lowest precedence. So sometimes I would write this without the parentheses, but whenever I think that it might create any kind of confusion, it's just better to add more parentheses. Okay. So now we can talk about proving our very first theorems. So what does it mean when we're proving a theorem? When we're proving a theorem, we're basically saying a proposition, and we're saying that this proposition is always true. Okay, so let's give a name to these kinds of propositions, and we call these tautologies. So a tautology, it's just a proposition that is always true. Okay. And whenever I'm proving a theorem, I'm basically showing that a particular proposition is a tautology. So here's one example. It's a very strange example. P and not P implies P. Now, think about what's happening here. P is some atomic proposition. I'm saying if both P and the negation of P hold, then P holds. But what I've written here is already impossible. It's impossible that both P and negation of P hold. But we already talked about this. We said that if I'm promising something and the conditions of the promise cannot be satisfied, then the promise is kept by default. So this is actually a tautology. Okay, how can I do this? How can I prove that this is a tautology? Well, let's just create that table again. So here I just have one variable. I have only one proposition P. So this proposition P can either be false or true, 0 or 1. Now, what happens to not P? If P is 0, not P is 1. If P is 1, not P is 0. Okay. Then what happens to P and not P? So you see, if P is 0, P and not P would be 0 and 1, which is 0. If P is 1, P and not P would be 1 and 0, which is 0. Okay, so P and not P is always false. Okay, finally, P and not P implies P. Okay, in this case, P and not P is 0, and P is also 0. So this one takes the value 1. In the second case, P and not P is 0, but P is 1. So this also takes the value. So you see, I have a particular statement here. By the way, I use the words statement and proposition interchangeably, so they mean the same thing to me. So I have this statement or this proposition, and this proposition always gets the value true. It's a tautology. So now I call this a theorem. I say that I just proved that this proposition always holds. Okay. Now, what is the opposite of a tautology? If I have a proposition that is always false, I call that a contradiction. Okay. So a contradiction is just a proposition that is always false. Now, if there is one thing you should know about me, it's that I'm super lazy. So that's why in this example, I already put a contradiction so that I don't have to draw another table, right? So if you look at P and not P, its value is always 0. This is a contradiction. Okay. Great. So we have these things, and you might think, well, what's the usefulness of these things in general? And by the way, this is what we call a Boolean algebra. So these are the operations in a Boolean algebra. Boole was the first person to formalize these things. So how can we actually use these in computers? The interesting point is that because in computers I have bits, I have zeros and ones, I can use these operations to design hardware that actually does computation for me. So, for example, let's say that I have some sort of hardware that does these operations that does negation, disjunction, and conjunction. Forget about implication, we will come back to it later. Okay, so these are actually called logical gates, and they're pretty easy to implement using just wires and electricity. Okay, so let's say I have these kinds of gates, and I'm not going to use the normal notation that they use in electrical engineering because I'm a mathematician. So I'm going to use the mathematics notation of this. So let's say I have an AND gate, and basically this is a piece of hardware that gets two inputs, and these inputs, you can just think of them as wires, and each of them will either have current in them or not. And it will give one output. And this output will have current in it if and only if both of them have current, both of the inputs have current. So it basically computes the AND. Okay, I can have another gate similarly that computes OR. And let's say I have another type of gate that computes negation. Now this one is a bit weird, because if you think about it physically, if the input doesn't have any current, how is it that the output can actually have current? Right, so where is it coming from? Basically, the way we think about this is that all of these have some extra input as well, where they can basically get their current from there. So, but because, again, we're mathematicians, we don't care about physics. So this magical gate can do negation. Now, if I have only these three operations, can I create other useful operations using them? So for example, you've probably programmed in some programming language already. Let's say you've programmed in C or C++. You've seen 32-bit integers. And you've seen that you can add two 32-bit integers together. Okay, so that addition operation has to somehow happen in your processor. So how does the processor actually do addition using a combination of these operations? Okay, let's do a very simple case. Let's say that I'm working with numbers that have only one bit. So I have only 0 or 1. And I want to do addition. Okay, what happens in that case? So basically, I have this. 0 plus 0 should be 0. 0 plus 1 should be 1. 1 plus 0 should be 0. And 1 plus 1, the problem is that this doesn't fit anymore because I have only one bit. I cannot represent 2. So I will just represent the last bit of the input. So I will just represent 0 here. Okay. Oh, sorry, that was wrong. Yeah. It's 0 because I'm terrible at math. So 1 plus 0 is 1. Yeah, and 1 plus 1 is 0. By the way, I'm a theoretical computer scientist. I cannot calculate anything in my mind. So you'll see this very often in my lectures. So let's say I want to implement this. Now, some of you might recognize this operation as XOR. This is taking the exclusive OR of the two, right? So let's say that this is my first variable or my first proposition X, and this is my second proposition Y. And what should I put here? So what is some expression that would compute this? So I can do this. I can say, look at X or Y and not X and Y. Right? This will give me exactly the result that I'm looking for. So the first part is 1 only when at least one of them is 1. And the second part is 1 only when both of the inputs are 1. Right? So this X and Y is 1 only if both of them are 1. So not X and Y is 1 if at most one of them is 1. If it is not the case that both of them are 1. And X or Y is 1 if at least one of them is 1. So what I want here is that I want a 1 if exactly one of the inputs is 1, right? So I say, make sure that at least one of the inputs is 1, and make sure that both of them are not 1. That's basically what I'm saying. Okay. We call this the exclusive OR operation. Sometimes we show it like this. Sometimes some people show it like this. It's OR with a line below it. But I could also just define this as a separate operation. I could just say, instead of writing this whole formula, I could say I have again PQ and P XOR Q. And this is how I'm defining it. I'm saying, let's look at 0 XOR 1 is 1, 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0. Okay. I could just define this operation like this. But what I'm showing you here is that if you have some sort of hardware that can somehow support these 3 operations, then you can combine them to support this operation as well. Okay. So more specifically, I can create a circuit using these gates that I had for AND, OR, and NOT, and I can create this XOR. So let's say I have a wire here that has X in it. So basically this wire has current if X is true. It doesn't have current if X is false. And I have another wire that has Y in it. Okay. Now first, I create an OR gate, and I put both of these as inputs. Okay. I'm also not really good at drawing. And then I create an AND gate. I also put both of these as inputs. Okay. Then I have a NOT gate, which only has this AND gate's output as input. And finally, I have an AND gate, which gets both of these as its inputs. And whatever comes out from here, this is X XOR Y. Okay. So this is X or Y. This is X and Y. So this one is not X and Y. And this one is X or Y and not X. Okay. Now, let's make it more interesting. What happens if instead of just 1 bit of input, I can have 2 bits of input? Okay. So my numbers here, they were binary numbers of length 1. Let's say I can have binary numbers of length 2. So I can have this X, which is now 2 bits. So let's say 1, 1. And I can also have Y, which is, let's say, also 2 bits. Let's say it's 0, 1. And I want to add them together. Now, what is the result of this addition? So this is addition in base 2. 1 plus 1 is 2, so 0, and then 1 comes here. And 1 plus 1 is again 2, so 0, and then I will have a 1 here, but it doesn't fit. So actually, the result of the addition is 0. Which makes perfect sense. Okay, so this is one case. Let me give you another example. Let's say I have 1, 0 plus 0, 1. In this case, I add them, and I should just get 1, 1. Now, basically, I have to break this down into bits. So my X is going to now have 2 different bits. Let's show them from right to left by bit 0 and bit 1. And Y is also going to have 2 bits. Let's say this is bit 0, this is bit 1. Okay. Now, the solution that I'm going to give you here, it's not optimal, but it's one solution. I just want to show you that a solution exists, that I can actually do this kind of addition using only those simple operations that we've seen before. Okay, so here's the thing. Remember, this is X0, this is X1, this is Y0, this is Y1. Okay, so I first try to add X0 and Y0. Okay, and I know that the result of adding them would give me the first bit of my answer. So let's give a name to my answer. Let's call this Z. And again, as before, this is Z0, this is Z1. So what do I know about my Z0? It should be exactly the result of adding the first two, the first bits or the rightmost bits of the two numbers. Okay, but I already know how to do that. This is how I can do that. Okay, so this is just going to be X0 XOR with Y0. And I know how to do that because I've already created the circuit. Okay. What about the second character? What about the second bit? So the problem here is that I have X1 and Y1, and of course I should add them together, but I might also have something that is carried from the right digit, right? So if both of these guys were 1, I added something, and I have to make sure that I do the carrying. Okay, so let me define some intermediate variable or some intermediate proposition that basically says whether there is a carry forward. Okay, so let me call that C because it's for carrying forward. And when will I have to carry something to the left? Only if both of them were 1, right? So C would just be X0 and Y0. So only if both of them are 1, I have to carry something to the left. Okay. Now, what can I say about Z1? What is Z1? X1, XOR Y1, XOR Z. Yes. So again, this is just addition in 1 bit, and I already know how to do it. The only difference is that now I have 3 different elements that I have to add, but I can just use the addition twice. And my addition was basically XOR. So this is just going to be X1 XOR with X2 XOR with C. Okay. Nice. Now, if I wanted to expand this whole thing, basically Z1 is X1 XOR with X2 XOR with this expression here. So X1 XOR with X2 XOR with X0 and Y0. And then I can also expand the definition of XOR according to this one, but life is too short, so I'm not going to do that. Okay. But at the end of the day, the thing that is important is that I can write this whole thing as just a combination of these operations, of these gates. So as long as I have some sort of hardware that can do AND, OR, and negation, I can do addition of 2-digit binary numbers. Now, I hope you agree with me that I can extend this to any number of digits. So I can do 32-bit addition, I can do 64-bit addition. If you don't agree with me, just do it and you'll see that you can do it. So this is the main reason why these kinds of operations are actually important in computer science. But this is a mathematics course, so we're not going to talk about these things a lot. We're just going to go forward with our logic. So now let's talk about something else. Let's talk about equivalence, or well, to be more exact, logical equivalence. So I say that two propositions are equivalent if they always have the same truth value. So if they're always both true or always both false. Okay. So if I have two different, let's say, I say two statements or two propositions, phi1 and phi2 are equivalent if, well, I want to say that they should always have the same value, the same truth value, but the way I can say that is this. I can say phi1 implies phi2 and phi2 implies phi1. Okay. And I want this to be a tautology. So if this thing is a tautology, then I say that phi1 and phi2 are equivalent. Okay. Now, we also have a name for this thing. This is phi1 if and only if phi2, right? And when two statements are equivalent, actually we write it like this. We write phi1, it's like kind of a thicker arrow. So don't confuse these two things. So the first one up here, this is another statement, another proposition. It's basically a promise, but it's a promise that has two parts. I'm promising that whenever phi1 holds, phi2 holds, and I'm also promising that whenever phi2 holds, phi1 holds. This one is a bit stronger. I'm saying that this first one is a tautology. I'm saying that this first one will always have the true value. Okay. So honestly, a lot of textbooks just don't really talk about the distinction between these two, and it doesn't matter that much, but it's a little bit different. Okay. Now, sometimes, again, there are textbooks that use a different notation. They use this notation to say that they're equivalent. This would probably make a little bit more sense. Now, the interesting point is that if you have two formulas in general, or in this case, two propositions that are equivalent, of course, you can replace them with each other, right? So let's see some examples of logical equivalence. So this is the examples. This is the first example. P then Q is equivalent to not P or Q. Can you prove this? Yes. So the easiest or the hardest way to prove this is to just do the truth table. So I have P and Q, and then I can look at P implies Q, and I can look at not P or Q. Okay. If P is 0 and Q is 0, P implies Q is 1. But here, not P will also be 1, which means that not P or Q is 1. If P is 1 and Q is 0, P implies Q is 0. But here, not P is 0 and Q is also 0, so not P or Q is also 0. If P is 0 and Q is 1, then P implies Q is 1. But because Q is 1 and this is OR, having 1 on one side is enough, so I will have 1 here as well. And this case is also very similar. So this is 1 here and 1 here. So as you see, these two expressions, these two different statements have the same truth values, so they're equivalent. Now, later in this course, we will stop doing truth tables, and you will never have to do a truth table in any kind of exam, because of course, this is brain dead. This is too easy and too hard at the same time. A lot of efforts, but no brain power. Okay, so what is the intuition here? The intuition is that on one side, I'm promising that whenever P holds, Q will also hold. So if P holds, then Q holds. That's my promise on the left side. What is my promise on the right side? The promise on the right side is that either P does not hold or Q holds. And again, this is not an exclusive. Okay. You can pretty much see that these are the same promises, right? So what am I saying here? I'm saying either P does not hold, in which case my promise is fine, or in the other case, in the case that P does hold, then Q also holds. My promise. But this is exactly saying the same thing. This is saying that if P holds, then Q holds. So it makes perfect sense. Okay, So in this course, we always have our intuition, but the intuition is not a proof. If I ever ask you for a proof of this, this is the proof. Okay. Great. So let's do some more examples. And by the way, these are all very famous equivalences. So what happens if I take negation of P and Q? I say that this is equivalent to not P or not Q. Okay. Again, the intuition. On the left side, I'm saying it is not the case that both P and Q hold. Okay. On the right side, I'm saying P does not hold or Q does not hold. Again, you can see that I'm making the same promise on both sides, right? So on this side, I'm saying it is not the case that both of them hold. On this side, I'm saying either P does not hold or Q does not hold, or neither of them hold, right? So again, I can do the truth table thing. So I have P, I have Q, I have negation of P or negation of Q. This is getting really painful for me. I hope this is the only session we're doing these things. So if P is 0 and Q is 1, then negation of P is 1 and negation of Q is 0, so their OR is 1, right? If P is 1 and Q is 1, both of the knots are 0, so their OR is also 0. If P is 0, then not P is 1, then not P OR with anything is 1. If Q is 0, then not Q is 1, so anything OR with not Q is also 1. Okay, and you can see that this is very much the knot of P and Q. So let's just do P and Q. So if I look at P and Q, 0 and 1 is 0, 1 and 1 is 1, 0 and 0 is 0, 1 and 0 is 0. And as you see, these two columns are exactly the negation of each other. Okay. So if I have knot of P and Q, I will have 1, 0, 1, 1. And then this column is the same as this column. So these two statements are basically equivalent. I'm going to give you some more of these statements. I'm going to give you the intuition, but I'm not going to do the tables anymore. So hopefully you will just agree with me about this. And if you don't believe me, then you can just do the tables yourself. And okay, so this was taking the knot of an AND, so the negation of a conjunction. Now we can also take the negation of a disjunction. So what is knot of P or Q? Okay. This is just going to be not P and not Q. Okay. Oh, I needed 3 lines there. Now you can again do the table, but the intuition is this. On this side, I'm saying I'm promising that P or Q is false. Okay, but when can P or Q be false? It's false only when both sides are false, both P and Q are false. But that's exactly the promise that I'm making on the right side. I'm saying P is false and Q is false. Okay. So these two are equivalent. But now, one question that I hope someone would ask, but everyone is too shy, no one's speaking, is this. I told you that, where is it? I told you that this is called the Boolean algebra. So why is it an algebra? What does it have to do with our normal understanding of an algebra? So if you think of how you're working with numbers, you have addition and multiplication. So here we have disjunction and conjunction. And somehow you can think of disjunction as a form of addition, and you can think of conjunction as a form of multiplication, right? So actually, you can think of conjunction as literally multiplication, because if you just multiply these, you will get exactly the values that you want. So if you consider these truth values to be numbers, conjunction is exactly the same as multiplication. But in this case, you have a weird case where 1 + 1 is 1. Okay. So that's why it's called the Boolean algebra, because of course the definition of the operations is different. But now we have some properties in basic algebra with integers or algebra with reals, and we wonder if we can have something similar here. So for example, I know that if I take A times B plus C, that would be A times B plus A times C. Right? This holds for real numbers and also for integers. By the way, at some point in this course, we're going to prove this for integers. But for now, I'm just assuming that you know this. So do we have something similar here in this algebra? So if I have something like this, if I have P and Q or R, what can I say about it? What is it equivalent to? I say that it's equivalent to P and Q or P and R. Now, again, you can build the table. The table is bigger now because you have 3 different atomic propositions here. So you will have a table with actually 8 rows. But can we also get an intuition? Why does this hold? So on the left side, I'm making a 2-part promise. I'm saying that first, I promise that P holds. And second, I promise that at least one of Q and R also holds. Right? But if I'm promising that P holds, I'm just promising that P holds it in any case, right? So I can just distribute my promise. I can say that it's one of these 2 cases. Either P holds and Q also holds, or P holds and R also holds, which is what I'm promising on the right. Okay. Again, this is not a mathematical proof. The mathematical proof would be the truth table. And you can do the truth table and you can see that it works. But interestingly, I can also distribute this way. I can say, what if I have P or Q and R? This also distributes. This is P or Q and P or R. Why does this hold? So again, think of it as a promise. On the left-hand side, I'm making a 2-part promise. And I'm saying at least one of these 2 parts holds. The first part is P. The second part itself has 2 parts, Q and R. So the second part of my promise is that both Q and R hold. Okay. So what does this mean? So again, let's just imagine this is my promise. What I'm saying here is that either P holds or both Q and R. Okay. So I want to break it down into 2 promises. And this is the way that I'm doing these 2 promises. Now, here's the thing. I can just do a case work on P, right? So look at the promise on the left. If P holds, my promise on the left definitely holds. If P is true, I have kept my promise on the left. Okay. But if P is true, I have also kept my promise on the right because I have P in each of these parts. So both of these conjuncts are going to be true. So when I take their AND, that's also going to be true. Okay. So in the case where P is true, these 2 are going to be the same. Now let's do the case where P is false. If P is false, my promise here would basically be Q and R. But if P is false, false or with anything is just that thing, right? So this is basically just Q and P, Q and R, sorry, which is exactly what I had here, Q. So you can see that my promise, which was 2 parts, I was saying at least one of these 2 parts holds. I can turn it into a promise where I say both of the parts hold, but now I have P or Q here and P or R here. Okay, again, this was just intuition. The proof is the truth table. Okay, what else? Let me see what else I can do. Well, we can also do some easy things, right? So we can do something like this. What happens if I take negation twice? Negation of P is equivalent to P. Okay, I'm not even going to talk about the intuition for that. We definitely have the intuition. There are some other pretty easy ones. So this one, for example, you can move things around, or it's commutative. Basically, P or Q is the same as Q or P. And P and Q is the same as Q and P. Right? Again, I'm not going to prove these things. These are really easy. We have some more. Yeah, I can do, well, we have associativity basically. So if I have P or Q, all of it ORed with R. This is the same thing as P or Q or R. So basically, if I have a bunch of ORs, I don't need to put the parentheses because it doesn't matter how you interpret it. It's going to give the same result. The same for AND. Okay, so P and Q and R is the same as P and Q and R. And by the way, the same holds for XOR as well. And I think I kind of used it here when I just wrote these XORs without putting any parentheses because the order doesn't matter. Okay. There are some other really easy ones as well. So for example, P or P is equivalent to P. P and P is also equivalent to P. But the interesting ones are the absorption laws. So what happens if I have P or P and Q? What is this equivalent? So I'm making a 2-part promise, and I'm saying at least one of these 2 parts hold. And then on one part, I'm promising P. On the other part, I'm promising both P and Q. So I'm making 2 promises, but one of my promises is much stronger than the other one, right? So I can just keep my weak promise. So this is actually equivalent to P. Okay. Now, I think I have to do a truth table for this one. So get ready, P, Q, and then we have P or P and Q. So 0, 1, 0, 1, 0, 0, 1, 1. So if P is false and Q is false, then everything here is false. If P is true, then P or something is true. If P is false and Q is true, then here P is false. So this is going to be 0. And P and Q is also false because P was false. So this is false or false, it's 0. And if both of them are true, you can check that this is also true. And as you can see here, this column is exactly the same as the P column. So P is equivalent to P or P and Q. Okay. What if I have P and P or Q? What can I say there?
It's also going to be the same.
Yes, this is also P. Look, again, the intuition here is that I'm making 2 promises, but this is a conjunction. So I'm saying that both of these promises hold. My first promise is P. my second promise is either P or Q. But if I've already promised P, that's a much stronger promise, right? So I don't even need to make this second promise. It's just the same as nothing. Again, this is the intuition. The proof is that you just create the table, you check that it's the same. Okay. Great. What else? Yeah, these are called the absorption laws. Let's say I have a tautology. So I use big T to denote a tautology. So let's say big T is a tautology. And let's say big F is a contradiction. Okay. So big T is some statement that is always true. Big F is a statement that is always false. Okay. What happens if I take OR with big T? So if I take P or T, what is this equivalent to? T. What if I take P and F? This is equivalent to F. And this is pretty much the rule that I was using here, right? So whenever I was evaluating OR and I saw that one side is 1, I wouldn't even bother evaluating the other side. And whenever I was evaluating and one side was false, I wouldn't bother evaluating the other side. I know that it's already false. By the way, this is also what a lot of programming languages do. So if you write C++ code, and let's say you have a conditional, you have something like this. You have if something and something else. It checks the value of the first one, and if it's 0, it doesn't even bother checking the value of the second one, because it knows that the whole values are the same. Okay, so this is called short circuiting, and it's based on these rules. Okay. Now I'm going to show you something kind of weird. This is something that people usually don't think about. So let's say I have a statement, and let's say that my statement is just a combination of atomic propositions and also this T, big T, and big F. And let's say I have the 3 standard operations. I have and, or not. I can define a dual, okay? So this is what I do. I say, let S be a statement or a proposition. And I just want to go over S, and I want to replace, let me see. Yes, I want to replace all the ORs with ANDs, and I want to replace all the ANDs with ORs. Okay, so, and then I call that the dual of S. So SD, or the dual of S, is the statement obtained by replacing every AND with OR, and with OR, and every OR with AND. Okay, in S. But I'm also going to say that whenever I see T in S, I replace it with F. Whenever I see F, I replace it with T. Okay, this is how I'm defining the dual of a particular formula that gives me a statement. So for example, let's say I have a formula, X or Y and not Z. Okay. Let's say I also have and T. Of course, and T doesn't do anything, but I just want to put it there. So if this is S, the dual of S would just be the same thing, but I'm replacing the OR with an and I'm replacing the and with an OR. Okay, let me put this parenthesis here as well, just to make sure we have the same understanding of what this is. But if I have not Z, I just put the same thing. So not Z, but true becomes false. Okay. So this is how I'm taking duals. Here's what's very interesting. I say that if I have two different statements, S and S prime, then S is equivalent to S prime if and only if their duals are equivalent. By the way, the dual is not really the negation. The negation is a very different thing. Of course, if S is equivalent to S prime, the negation of S is also equivalent to negation of S prime and vice versa. But I'm not talking about negation here, I'm talking about the dual. And the dual was something that I'm getting just by these replacements. Okay. Now, how can you prove such a thing? You have to basically consider all the different ways that you can make new statements by combining the previous statements using these operations. Okay. I'm not going to give you the proof right now because we need structural induction. So very soon we're going to talk about induction and then we will come back to this and we prove this. Okay, but it's a very interesting fact. Okay, what else can I give you here? Yeah, I'm going to give you a link to this book and you can read the book, which has tons of examples of this. I don't believe it. It's like 50 pages of these easy things. And you can read all of them. But I'm not going to spend too much time on this now. Let me just skip over all of this. Okay, yes. So now we want to talk a little bit about what we call rules of inference. Okay. So I already talked about this idea that a theorem is just a proposition that is always true. That is a tautology, right? But that's not usually how theorems look like in mathematics. If you look at the way that you write theorems in, let's say, basic Euclidean geometry, the way it works is that you always have some hypotheses or some premises, and then you have some conclusions or some results, and you want to prove that these hypotheses give these conclusions. Okay. But that's easy to write in our format, right? So I can have something like this. I can have H1 and H2 and so on to Hn. All of them together imply something. Okay, imply, let's say, C. So hypothesis 1, hypothesis 2, hypothesis n, if I have all of them, then all of them together imply some conclusion C. And if I show that this is a tautology, I have basically proven a theorem that says if H1 and H2 and Hn all hold, then C holds, right? But we want to have an easier way of writing these things. And the easier way that we have for writing these things is basically giving us a definition of what a proof is. So if I want to write a proof for something like this, I can always just do a huge table. Right, but my table would be super huge because in this case, I have n premises, so I have to put 2 to the power of n different rows in my table. It's going to be super painful. Now, another way to do this is to make sure that I can just create new, and let's say I have some rules that help me create new tautologies from the tautologies that I already know to exist. Or another way of looking at this is that I'm taking these hypotheses, I'm thinking of them as some sort of an axiom. And I'm saying that if I assume these are always true, what are the other things that I can get? Okay. So here's what we can do. We can say that, well, I'm going to just write a bunch of things here. I'm going to have a sequence of statements. And I'm going to call that a proof. So a proof for this thing, for H1 and H2 and so on to Hn implies C is what? It's just a sequence of statements, basically a bunch of things that I'm proving. Is a sequence. And let's write this sequence like this. Let's write it as P0, P1, P2, so on to Pn. And this last one, well, it's N, because N was the number of hypotheses that I had. So let's say Pk. And this last one should be exactly C. Okay. So it's a sequence like this, such that for each Pi, I have one of these two cases. It's either that Pi is one of my hypotheses, so Pi equals Hj for some j, or that Pi can be obtained from the previous things that I have written in my proof. Okay, so I have P0 and P1 and P2, so on to Pi minus 1 imply Pi. And this should be a tautology. Okay. This is what I call a proof. So whenever I ask you to prove something given some hypothesis, what you can do in your proof is that you can use any of the hypotheses as one line of your proof, or you can use a new statement as long as you can deduce that statement from the things that you have proven so far. Okay. So we somehow need rules that would allow us to prove this part actually, right? Because at the end of the day, what I want to make sure is that I don't have to create any of those horrendous truth tables, right? And of course, now I don't have to create a truth table for the whole thing that I want to prove. But the problem is that in this part 2 here, I'm saying that P0 and P1 and Pi minus 1 imply Pi. So it cannot be that the only way I can show this is again by truth tables, because if that's the case, again, my proofs will look very terrible, right? So I want to have some rules for this part 2. And these are what we actually call rules of inference. And to be honest with you, only one rule is enough. And later in this course, we will see that all the other rules can actually be obtained from this one rule. But for now, I'm going to give you several rules because it makes your life easier. So this is the first rule. The first rule is that if I have P and I have P implies Q, I can have Q. Okay. First of all, what does this notation mean? When I'm writing something like this, I'm writing a rule. I'm saying that whenever you have these two statements in your proof, you are allowed to also add this statement in the proof. Okay. So if you have a proof, and somewhere in your proof you have already proven P, and somewhere else in your proof you have already proven if P then Q, then you can combine this and you can add Q to your proof. Okay. Now, again, depending on the textbook that you use, some people also put 3 dots there. I don't know what's the point of those 3 dots. It doesn't really help anything, so I don't put it. Okay. So this has a fancy Latin name. It's called modus ponens. I have no idea what that means. All I know is that it means this. So whenever you have these two things, you can just put this. But this is basically just another way of writing a tautology. All I'm saying here is that if I have something like this, if I have P and P implies Q, then this whole thing implies Q is a tautology. Right? So what is the reason that if I prove P and I prove P then Q, then I have already proven Q? It's because no matter what these two statements are, this whole thing is a tautology. So whenever both P and P then Q hold, then Q also holds. So basically the idea is that we create the truth table only once, only for this expression, and we check that this is a tautology. And then we just use it as a rule so that we can just apply it to our different statements and we can create a proof. Okay. Now, we can also have other things. But again, as I told you, these are not really necessary. So I can have this. If I have P implies Q and Q implies R, then P implies R. Okay. Again, all you have to do is to write it as an implication right like this and show that it's a tautology, and then you can use it as a proof. Okay. So the implication here, again, this is a bit hard to write. So P implies Q and Q implies R. All of it together, I don't need these parentheses, by the way, implies P implies R. Again, you can just do a truth table and make sure that this is correct, and then you can use it in your proofs. Okay. Great. So now we have a nicer way of writing proofs. Whenever I give you some premises and I tell you to prove something given these premises or this hypothesis, all you do is that you generate a sequence like this. And at every line of your proof, you can either use one of the hypotheses or you can just apply this rule to two of the previous lines, or you can apply this rule to two of the previous lines. Okay, let me give you just one more rule. So let's say that I have proven P implies Q, and let's say that I have also proven not Q. What does this mean? So I have proven that whenever P holds, Q also must hold. I have also proven that Q does not hold. So I have effectively proven that P does not hold either. Right? So I can also have this rule, not P. Okay. This one has another fancy name. This is modus tollens. I don't speak any Latin. Okay. Yeah, and again, the reason it holds is that you can write it as an implication and you can check that it's settled. Okay. Great. So this is it for now. In the next session, which is actually this afternoon, you guys are going to love your Mondays. This afternoon, we're going to talk about first order logic. So we're going to add quantifiers to the logic that we have so far, and we're going to design integers. So see you in the afternoon.